Okay, now I want to talk about vapor pressure and get to a relationship for pressure and vapor pressure. Okay, so the vapor pressure is defined as the pressure of a vapor in equilibrium with its liquid. Now, pretty soon we're going to have mixtures, but at this point we're still in pure systems. So here you have a liquid, and it has a P vapor, and I'm going to put a star here indicating that this is the vapor pressure of the pure material. Okay. Actually, sorry, not the pure material. This is the vapor pressure. So P vape star equals no change in external pressure. And this will make sense in a second. Okay, so here you have atmospheric pressure pushing down, force per unit area. All right, you've got 14 pounds per square inch pushing on you right now, 1 atmosphere. So the vapor pressure here is going to represent, there's going to be a few atoms or molecules. They won't be atoms, they will be molecules. There are going to be a few molecules in the vapor phase right above the surface of the liquid. And there's going to be an equilibrium between them going into the vapor phase and them going back down into the liquid phase. That equilibrium is, so the pressure of these molecules above the liquid define what the vapor pressure is. Only those are in equilibrium with the system or with the external pressure. So if P atmosphere is greater than P vape star, it's going to stay a liquid. Okay, so this means P vape is, or P atmosphere is much, much bigger, big arrow. It's going to be pushing all of these molecules down back into the liquid phase. You're going to have it stay a liquid. If, however, this P atmosphere is less than P vapor, let's say it's like a little bitty arrow, then what's going to happen to the molecules in the liquid phase? They're going to go up into the vapor phase, and you're going to have a higher number of them in the vapor phase than you will in the liquid phase. And so you're going to have a volatile compound. Okay, this is benzene's volatility is much higher than 1 atmosphere, is why it always evaporates quickly. Same with acetone. Whereas mercury has like no vapor pressure whatsoever, so it stays the chunky mercury liquid in 1 atmosphere. Now, if P atmosphere is equal to the vapor pressure, then this is where you have phase transition or boiling. Okay, so there's no difference between the two, equal and opposite forces, so these things are just going to vaporize out. Okay, now the equation that we're getting to is what happens if we change this pressure. I have it listed as 1 atmosphere, but what if it's different? Okay, so when it's 1 atmosphere, we've got P star. Cool, P star. But it's going to change P, and I'm going to call this P new, and this is the new vapor pressure when external pressure changes. Okay, so let's say I take my beaker and I go up the top of the mountain and I'm like, okay, now how does the vapor pressure change because my external pressure is different? Do these rules still hold? The answer is kind of, it depends. Because this is going to follow a formula to where we take the original P vapor with no change in external pressure based on 1 atmosphere, based on standard conditions, and we multiply it by E raised to the power Vm of the liquid phase. This is the molar volume of the liquid, multiplied by delta P, the change in the pressure, all that divided by RT. Okay, so this is the change in external pressure. Okay, so this is our new function. P, the new vapor pressure is P star, the original vapor pressure, multiplied by this exponential. Cool? What does this mean? Well, this means as this number gets bigger, delta P goes up, we have the change and the P vaporization, or the vapor pressure is also going to go up. Right? So I'm going to show you how we get this. This is the goal. Cool? Groovy. Okay, the reason I'm showing you this derivation because I think it would be helpful to link the mathematics to what we're trying to describe. Okay, so what do we know? Well, at equilibrium, the chemical potential of the liquid is going to equal the chemical potential of the gas phase. So here's my liquid phase, here's my gas phase, and we're trying to monitor or come up to a way to quantify the vapor that's right above that liquid. Okay, so we know at equilibrium, these two things are equal at equilibrium. Okay, which means that the change, any change that happens in d mu is going to be the same change that happens in d mu for the gas. So d mu liquid must equal d mu gas for equilibrium to be maintained. All right, we also know that d mu dp at constant T equals molar volume, bonus, which means I can then say that d mu of the liquid is equal to V sub m of the liquid multiplied by dp. Okay, so what I've done now is I've taken this and I've broken it down, and I've taken this dp and I've now multiplied it by the molar volume. Okay, and now this is stressing at constant T. Constant T. But what do you know about a phase change? Constant T. Okay, so the temperature is going to be constant, so we're guaranteed that this temperature here is going to remain constant, which means is that's when we can make that mathematical step of taking dp and putting it over into the right-hand side. Okay, likewise, I can do the same thing. d mu of my gas is equal to the molar volume of my gas, dp. Again, at constant T. Cool? All right, well, we know that for a gas, we can assume ideal behavior, which means V sub m is equal to RT over P. Isn't that snazzy? And then what we can do, everyone following me? Okay, so we know from our equilibrium condition that these two are equal, which means d mu of liquid is equal to d mu of my gas, which means now I can say Vm of my liquid dp is equal to is equal to RT over P dp. Cool? Okay, I'm going to erase this so I have a little bit more room. Remembering that Vm equals RT over P. Okay, so now I want you to notice how we've got Vm is the liquid dp, RT over P dp. Cool? All right, so here's where it gets a little tricky. Now we're going to integrate both sides because I want to know what the whole sum of all of these options are across all of the different pressures. Remember what we're trying to do, which is get a relationship between how the vapor pressure of this liquid is going to change as we change the pressures. So knowing how we change pressures is knowing what our limits of integration are going to be over how much we actually change the pressure. Okay, so I'm going to go from P star. This is the original pressure that of 1 atmosphere, or the original vapor pressure of which I'm comparing. And I'm going to go from P star to P star plus some delta P. Okay, so I don't know how much I've changed pressure. I'm trying to keep that vague. And so to do that, I'm going to say, okay, well, there's my initial pressure, and I'm going to integrate to some different pressure, which means I've got now P goes to P plus something, right? And that P plus something is going to be P star plus that delta P, how much I've actually changed the system. Okay. Which means on this side, now the other thing to think about is we've got what each of these two sides represents. We've got the molar volume of the liquid, so that's the liquid phase, and it's experiencing this pressure of the external So P atmosphere is pushing down on it. This gas phase, however, this is the difference in the vapor pressure of the actual material. Okay, so this is representing the pressure of the vapor right above that liquid, which is the same as P star. That's where it starts with. But now what it's integrating to is the new vapor pressure, because the vapor pressure is not about the liquid, it's about those little gas particles up above the liquid in equilibrium in the vapor phase. Okay, so they're the ones that are changing. Their vapor pressure goes from P star, the initial same pressure that the volume of the, or the molar volume of the liquid is experiencing. And now we're going to, I'm going to call this P new. So this is the new vapor pressure. Go team. Okay, I'm going to erase this part so it's a little bit more clear with what I'm writing. Okay, so then when I integrate both of these sides, I get, well, this is an easy one. I've got V sub M L, delta P. Where P goes from P star to P star plus delta P. Equals, and this is going to be RT log. So I've got dP over P, which is just the logarithm of the pressure of P new divided by P star. Did everyone follow that? I went ahead and put in the limits of integration because it'd be log of P new minus log of P star. That is the same as the P new over P star. Okay. All right, so now we're going to have Vm of the liquid is equal, multiply that by P star plus delta P minus P star is equal to RT log P new over P star. Okay, so that's cool. P star plus delta P minus P star. That's awesome. Oops, actually this would be that. That means that this is just V sub M liquid plus delta P, because my P stars cancel each other out, is equal to RT log P new over P star. Okay, so then what we can do is we can now solve for P new, the new vapor pressure of the system upon an external pressure changing. All right, so in order to do that, let's see, we want to take this whole thing, VML plus delta P divided by RT. I've moved RT into the denominator of this side, is equal to log P new over P star. I take the exponent of each side and I'm left with, so exponent of this becomes just the function inside. And so that means that I've got P new over P star is equal to exponent Vm liquid plus delta P over RT. And then I can take this P star and I can move it to right there. And that's where I will get P star is equal to P new. So the new vapor pressure is equal to the original vapor pressure of the gas against the original pressure multiplied by the exponent of the molar volume of my liquid plus the change in pressure that I undergo divided by RT. Yay! Why did I think that was important? We are moving into different types of limits of integration. And so this is where it's important to recognize what you're integrating over. Before, when we were doing one component system, you have a gas and it's going to go through an adiabatic process and you watch the change in temperature and you're like, I'm integrating from T1 to T2. Great. But now we're going to have an integration limit that's going to be particular to the part of the phase that you're working with. So it's really important to make sure you monitor what system you're describing. Okay, so that's why I think this example is really important, because you have to be very careful in the bookkeeping of what is P star versus what is this P new versus what is this delta P. Okay. What else? Oh, really cool thing. So, oops, wait a minute. Oh, I totally made a mistake. Yee. Let's dive into where I made a mistake. I have V sub m log plus delta P. What are the units there? Can I add volume units to pressure units? Absolutely not. That's bonkers. I made a mistake. I saw this pressure and this plus sign here, and I was like, oh, okay, V sub m plus delta P. Totally wrong. Bad Allison. Or not bad Allison. Good Allison for noticing the mistake and always doing a unit check. Multiplication. The little X there. So my unit check that I was going to do was to make sure that my units cancel, because anytime you take the exponential of something, you want to make sure your units cancel. So I've got my volume multiplied by a pressure. So I've got, let's say meters cubed multiplied by kilopascals. That's great. That's the same as a joule divided by RT. That's a thermal energy. So I've got units of energy and units of energy divided by each other. Go team. It's also really cool to note that this is some value per RT. This is a foreshadowing to what we're going to get into with collision theory as well as kinetics involving transition state theory and what's called the Arrhenius behavior, where you've got this exponential value of energy here per RT. Okay, so this fraction has significant meaning. Cool. Okay. I think that's all I want to go to in this one. There's your equation. Yay. Now you can use it and plug it in. But it's important to recognize limits of integration. Bonus. Bye.